Alright, so I have made the model in HyperMesh, and I'm going to take a look at it and import it into ABAQUS CAE. So I do have these two nodes that I've identified as to where my knife edges would sit if this was a tensile specimen, exactly 1 inch apart, or 25.4 millimeters. And let's take a look at the file. Now, I did create two node sets in HyperMesh, one at this region for the bottom grip and one at this region for the top grip. Basically a plane of nodes that I'll constrain on the bottom completely, and then I will move in the vertical direction a millimeter to simulate an extension of this bar. Now, in the input file, which I'll call up here, here are the two node sets that I just mentioned, but I added these two by hand, the knife top and the knife bottom, 576 and 510. We'll remember those numbers, and those will help us figure out what the relative displacement is between those two particular points. So let's go through the process of importing this into ABAQUS CAE. So let's see, that's this window here. Now I'm going to import a model, and it's an INP format, and it's specimen 4. Okay, so there it is right there. And to avoid any confusion, I'm just going to delete this kind of default model that's in here. I do need to do a couple things. I'm going to create a material, aluminum, and we'll make this just an elastic analysis. We use the Newton millimeter in second system with 70 gigapascals, or 70,000 megapascals for the modulus of elasticity, and Poisson's ratio, we'll just call it 0.3. We do need to create a section, solid section, homogeneous, out of the aluminum material, and then we need to assign the section to all of these elements. Then we'll X out of this panel. Let's see. Here are my sets that I have. This one was created by ABAQUS. These are the ones that I brought in. We'll go into the step. In the initial step, we'll create a boundary condition on displacement, choosing the sets for the bottom grip, and we will constrain it in all three directions. We're going to create a step. It'll be a static general step. We can use a time period of 1. That should be fine. I always like to add a couple zeros under these increments. And in this, we're going to simulate a displacement controlled tension test. We're going to create another boundary condition on displacement using the set top grip. And we'll keep the displacement. We won't specify any displacement for, well, let's do this. Let's say U1 is 0 and U3 is 0. And U2, we're going to have a maximum displacement of 1 millimeter. We're going to create an amplitude card. We'll call it AMP1 tabular. And I have here a Excel file that I'm going to paste into here. So it has at 0.1 time, it goes to 0.1 millimeter, okay, for the amplitude, and here it is here. Now this is multiplicative. So if I put 10, then it would take the amplitude card and multiply it by 10. but 1 right here should be fine. Let's check the time for this step. The time period for this step is 1 second, so that should be fine. And we need some field output. We're going to go every x units of time, and we'll do 0.1 units of time. We have our stresses, strains, displacements, and the rest of this is kind of just the defaults here. I'm going to save this file. And I think we're ready to submit it. We're going to create a job based off specimen 4 model, and we will bump this up to 4 processors, and we're going to submit it. Hopefully it'll go well, but if we have any mistakes, we'll fix them soon enough. Alright, so it's working on generating the input files, and it says the input file has been submitted for analysis. We can monitor this. And here it's gone through the step time, and it got to time of 1, and that should be okay. So it looks like it's completed. So we'll look at the results, and just to check things out, let's look at the displacement, and we got a 1 millimeter displacement. Let's look in the U2 direction. Okay, so 1 millimeter. Let's see what kind of stress it is in the 2 direction. That's the axial direction. So it looks like it's 1096 megapascals. That might be kind of high. Maybe 100 megapascals would be better. So if we take this and go back to time step 1, which would be a 0.1 in time, then here we have 109.6 for our stress that's in the red upper end of the red zone. 109.6 megapascal. So that's a pretty reasonable stress for a tensile specimen. Of course, this being a purely elastic analysis, we can keep applying stresses until whatever number we want to get. A real material will fail or yield before it gets to any particular value. Alright, so we've set this job up and we've run it successfully. What I'm going to do in the next video is we're going to take a look and try to make sense of our numbers from our extensometer and try to illustrate why you really need to use an extensometer and not just use load displacement data off of the testing machine.